What is the formula for work done?
I was
Yes.
absent yesterday, sir.
Yesterday you said, sir,
Yeah.
like force into displacement.
Force into displacement, but the exact formula that was for your
Fx
grade
cos
9.
theta. Like
Yeah,
for
that is
scalar quantity,
Fs cos theta. Okay. So work done is given by Fs cos theta.
cos theta.
It is the, or we can also write it as F dot S. So it can be written as F dot
Arrow,
S.
ma'am.
Yeah. So this is the scalar product. We call it as the scalar product or dot product. Okay. So work is defined by F dot S, or we write it Fs cos theta. There can be a work can be positive work, negative work, or a zero work can be done. Now today we'll be discussing one more, that is work done as potential energy, work done as kinetic energy, and we will also discuss the potential energy of a spring. We'll discuss potential energy of a spring. Okay. So how do we discuss? How do we know about the springs? See,
Can you just
all
repeat the definition of potential energy?
potential energy. Okay. So potential energy is the energy stored in an object due to its
In
shape, position, or configuration.
energy possessed by an object.
Yeah. So energy possessed by an object.
An object.
Yeah. By virtue of its energy possessed by an object due to its position, shape, and configuration. Okay. So in your grade 9, you had seen about the potential energy stored in an object which is lifted to a certain height. Like suppose if an object is lifted to a height h, the potential energy stored by it will be given by mgh.
Yes, sir.
Yeah. So that we did in the case of gravitational potential energy. We specifically call that as gravitational potential energy. So we had obtained gravitational potential energy. Okay. So the gravitational potential energy again was given by the formula Fx, and it was equal to mgh. Not Fx, it was F times of S. Okay. So it was mgh, where mg was the weight, which that is the amount of force that we need to lift an object. That is the gravitational potential energy. Now, this here we observe that there is a change of position. An object changes its position from
Position.
one place to another. Okay, so if it is changing its position from one place to another, so then only uh, then there is a gain of potential energy in that object. We also observe some objects where there is no change, there is potential energy, but there is no change in the position. Rather, there is change of shape, there is change of configuration. Okay. For example, we observe a spring toy, where we observe that the spring can be wound if we wind the spring, which makes the toy to move. Okay. So we observe that when we wind the spring, we are changing the shape of the spring. And therefore, we observe that the spring has some potential energy stored in it, and that potential energy can be used to do work. Okay. So we knew that the spring has potential energy. We know that the arrow and bow also have potential energy. But how to measure that? So today we'll be measuring, first of all, the force on a spring. Okay. The force acting on a spring, and then we'll come to the potential energy of a spring. So we'll see force acting on a spring. So we call this force, whatever force is acting on the spring, whatever force act on the spring, we call that force to be restoring force. So see how it happens. Suppose we take a spring and we load this spring. So we load this spring with some weight. Okay. So initially, suppose without loading, the spring has some length L. So suppose at this situation, the spring has some length L. Now, if I load this spring with some weight, so the spring will extend, right? I have loaded it, and now the spring has produced some extension. Some extension is produced in the spring. Okay. Now, because of this extension, this extension is trying to pull this spring in the downward direction. Whatever weight I have put over here, so my weight that is hanging from the spring, it is making it go down. But the spring itself is trying to regain its original shape. As a result, the spring is making this object to move up. Like, it makes the object to move up. So here we have two forces acting on the spring. One is the downward weight, the other one is the upward restoring force set up in the spring. So the restoring force which is set up in the spring, the restoring force F set up in the spring is equal to the weight at this point when a certain extension is produced. So therefore, using the Hooke's law, we obtain that the restoring force F is directly proportional to the extension, and hence we obtain that the force will be equal to minus kx. So the force acting on the spring is given by F equals to kx, where x is the extension produced. Here x is extension produced. X is extension produced in spring, and k is the spring constant. This value k is called as spring constant. Okay. So k is spring constant. So the spring constant, it depends on material of the spring, what spring is being used for the extension. Okay. So on material, on thickness of the spring. So these are the geometry of the spring on which the spring constant depends. So it is constant for different springs. So I'm giving you just a small question, and we will try to do this question. Okay. I think Jaswant had joined and he is not there in the meeting. Just 1 minute. Also, Pritam, turn on your camera. So let's do this question. We have a force of 10 Newton produces an extension of, yeah, Jaswant, what happened? Jaswant and Dhanunjay, what happened?
So my laptop got
Writing.
off.
I didn't see the message.
Okay, Jaswant, you didn't see the message. Okay, your class is regularly at 4:35 sharp. Regularly means it's not on Saturday except all the 5 days we have a physics class. Okay, so here just since you both of you joined just now, you see here we have the spring forces. Okay, so I was expressing this spring forces. I'll just explain it once more that how much is the force experienced by a spring. And what happens if you load a spring? Okay. So let us see. We have a spring and let us say the spring has some length L. We have a spring and it has some length L. Now, if I hang some weight on this, so if I hang some weight, the spring will get extended. Okay, some extension will be produced in the spring, right? So here we have some extension will be produced in the spring if I hang some weight over here. Because as we know that weight is a type of force, and since it is a type of force, so weight is a force which is acting downward. It is pulling the spring in the downward direction. Okay, so as it pulls downward, the spring gets extended from its original position. The spring gets extended from here. So suppose some extension X is produced. Here we have some extension X produced in the spring. Okay.
Yes.
And if you are facing any technical issues during the class, okay, like maybe suppose your laptop is not working or any other issue, you can message in the group or you can message me personal over there. Okay. You also have a CT support and feedback group. I think both of you have joined over there in the support and feedback group. Yeah, Pritam and Dhanunjay, have you joined in the support and feedback group?
Oh, yes, sir.
Yeah. So if you are facing any issue, you can message in the support and feedback. Suppose sometime your power went off or anything happens of that sort, so do message over there. Okay. Even if you are not able to turn on the camera, so then also you should message in the support and feedback group. If you are facing any technical issue, if you are just 1 minute, I just hold on 1 minute. See, so when we hang some weight, we are applying some force, because of which some extension is produced in the spring. And when this extension is produced in the spring, so a restoring force is also set up in this spring. So we call this as the restoring force. Now, if suppose if there is no restoring force, then the spring would continue to move in the downward direction. Okay. So as the extension produces, the restoring forces are set up in the spring, and these restoring forces they stop it the spring's further motion. So at this point, you can expect that the restoring force will be equal to the weight or the weight that we have applied over here. So in this situation, the restoring force is equal to the weight, and hence I can write here that the restoring force F is equal to Kx. We write it as negative of Kx, as the restoring force acts in a direction opposite to the direction of extension. So we have taken here the direction of extension to be in the downward direction, but the restoring forces are acting in the upward direction. Okay. So restoring forces, they act in a direction opposite to the direction of extension. Hence we write F equals minus of Kx. Okay. The value K is called as the spring constant. Yeah, Jaswant, are you facing any issue? Jaswant?
So can you hear me?
Yeah, are you facing any problem?
Sir, so this is the automatic. I'm rejoining again, sir. Stuck in.
Okay, you are rejoining again and again. Okay. See, you can check, you can check your net speed, your internet speed you can check. Okay. Just through Google type your speed test and see you will be getting your speed. Okay. And if you are facing any issue during the class, so just message in the support and feedback group. Okay, just one. This is for all of you.
Okay, sir.
And any problem during the class or anything, yeah, you have to message in the support and feedback group. So for today, I'm sparing you. If you in the next class, coming class, whatever class is there, your camera should be on. If you're not able to turn on the camera because of the internet issue or because of the darkness, because of any other problem, so you just message in the support and feedback group so that uh, people will see that yes, you are not able to turn on the camera, right? So this is for all of you. I think Dhanunjay knows this better. So do follow it. So the restoring force will be given by F equals to minus of Kx. Now see, at this point, this downward weight is equal to the restoring force. Okay. So you can find out easily all the things. X is the extension produced in the spring. So depending on this, I am giving you one simple question here. So a force of 10 Newton produces an extension of 3 centimeter in a spring. Produces an extension of 3 centimeter in a spring. Find the spring constant. Okay, so your question is, you have two questions. First of all, you have to find the spring constant. So find the spring constant.
Okay, sir.
Okay. Find the spring constant, and the second one is how much extension will be produced.
Minus 3.3.
Okay. The next one is how much extension will be produced if a force of 35 Newton 35 Newton hangs on the spring. Oh. Do these two questions. In the first one, you have to find out the value of spring constant. Do mention the unit also. When you are finding the answer, do mention the unit of your answer. Like the spring constant, it will have the units Newton per meter.
There is the first one minus 3.3.
No, it's not minus 3. Use the SI system, convert the centimeter to meter. Okay, you got that minus 3.3. So do not include this minus sign. And that minus sign is just to represent that it is the restoring force. Okay, so you'll be writing, you can write it as 3.33 Newton per centimeter. Then you'll write it as Newton per centimeter, not as Newton meter. So for that, you convert the centimeter to meter, and then you will get your answer in Newton per meter. So if you convert the centimeter to meter, you will get your answer for the first one as 333.3 Newton per meter.
Okay, sir.
Then second one, I think you can find out.
You find it in Newton per meter.
Okay. So we got the value of spring constant, and then we can use this value of spring constant to find the extension for the second one. Okay. So for the second one, you again use the formula F equals to Kx. F is given as 35 Newton. K we know as we have got 1000 by 3 or 333.3 that you can write down. Multiply it by x. So we want x here. So we can add 35 multiply 3 divide by 1000 will be equal to x. Okay. So it's how much is the answer?
Find it.
Are we getting 0.105 meter?
Define.
Yes. Do we get the answer as 0.105 meter?
Yeah, so 0.105 meter.
Yeah. And if we convert this to centimeter, the answer would be 10.5 centimeter.
10.5 centimeter.
Okay. So the extension produced will be 10.5 centimeter.
Centimeter.
Now another simple question similar to this. So here you have the length of a spring changes from 10 centimeter to 12.5 centimeter when a mass of 50 gram hangs from it. So you have to find the spring constant. Find the spring constant. Then question number 2 would be find the extension produced if a mass of 122 Newton, 120 Newton, so 120 gram hangs from it.
Change.
So I hope you can do these questions. You know how can we convert mass to Newton? Yes, Pritham and Dhananjay, do you know how can we convert mass to Newton?
Hello.
Yes.
Yes, sir.
So are you able to, do you know how can we convert this mass into weight or in Newton?
Don't know.
No. Okay. See, in your grade 9th, you have studied that force is, or weight is the force with which gravity pulls an object. That is how we have defined weight. So we know that weight is nothing but force with which gravity pulls an object. So force with which gravity pulls an object. The force with which gravity pulls an object is called weight. Now, how do we find that force? So that force or weight we had studied in class 9, that weight is given by the formula mg. If here g is 9.8, which is acceleration due to gravity, 9.8 meter per second square, and m is your mass. M is the mass of the object in kilogram. So, can you convert this 50 gram to Newton? See, we have a mass given by 50 gram. So, how much Newton will it be? Dhanunjay, how many Newton? Yes, Dhanunjay?
50 by 9.8.
Okay. So it's not, it will, you will be, weight will be equal to, first we have to take mass in kilogram. Since mass here is in gram, which is just 50 gram. So we will take it in kilogram. 50 divided by 1000. That's kilogram. And multiply by G, which is 9.8. So you can do this, multiply this 5 with 9.8, divide by 100, you'll get the weight. So in this way, you will get the weight. And once you get the weight, then we can apply the formula again. Okay. So find out the weight, multiply this 9.8, multiply 5.
Why do we use that formula which you're using now?
Okay, this formula. See, if you hang the spring, if from the spring you hang a mass,
Hmm.
so which force is acting on this mass?
Gravitational force.
Gravitational force. And gravitational force is nothing but weight. See,
Hmm.
weight is defined as the force with which gravity pulls an object, right?
Yes,
So
sir.
the gravitational force is nothing but the weight. So hence we are finding out the gravitational force which is acting. So this gravitational force would be equal to mg, and this is the force which is producing the extension in the spring. So that we can use the formula F equals to kx. Okay. So you have 49.0 divided by 100, you get 0.49 Newton. So with a force of 0.49 Newton, an extension is produced. So the initial length at the beginning, the spring was 10 centimeter long, and after we hang the mass, its length becomes 12.5. So how much should be the extension?
2.5.
2.5. So we know here extension would be 2.5 centimeter. So hence we can find out the spring constant.
Yes.
Yeah. So find out the spring constant. And once you know the spring constant, then we can use that value of spring constant for the second expression. Okay. In the same way for the second expression also. So do this question. I will be checking your answer. Do it just now.
Sir, it should
Dhananjay
be
and Jaswant.
force as 0.49.
Yeah. For the first case, the force is 0.49
0.49. Yes, sir.
and extension is 2.5 centimeter. If you want to do it in Newton per centimeter, you can do it in Newton per centimeter, but it is advisable always to use the SI system of units. Okay, so it would be better if you convert it to meter. Convert this 2.5 centimeter to meter.
1.96.
You got your answer?
Yes.
So if you divide this, you will be dividing here 0.49. 0.49 will be divided by 0.025. You get
0.0.
19.6.
Sir, 19 point.
Yeah,
19.6.
yeah. So using this formula, F equals to Kx. If we use this, we get the value of spring constant K as 19.6 Newton per meter. And now we can use this to find out the extension produced again. Okay. So here we have the mass as 120 gram. So we can find out the amount of force that is acting in the same way. We know the spring constant and we can find out the extension. Okay. So what would be the answer then? Just once, and Dhanunjay, are you there?
Yes, sir.
Yes, sir.
Okay, so do the answer. I'm not getting any responses from your side.
120 grams.
Yeah. Yes. What the answer?
Mass will be 1.176. Weight
Uh, Mass is 0.12. Okay. And weight will be 0.12 multiply 9.8. So,
1.176.
okay. So maybe if I check, you will be getting 0.12 multiply 0.12 multiply 9.8. So you get 1.17. Okay. And this 1.17 divided by 19.6. If you divide it by 19.6,
0.6.
so you'll get the 0.06. Okay. So the
0.
extension that will be produced, extension produced here, X, you will get as 0.06
0.06
meter. Okay. And converting to a centimeter, you will get 6 centimeter extension. You will
centimeter.
have an extension of 6 centimeter.
Yes, sir.
So I hope you people have understood this concept of spring and forces.
Yes, sir.
So in the similar way, we will take up the potential energy stored in the spring in the next class. In next class, we will be taking the potential energy stored in spring. Okay. But I hope today you have understood how do we obtain, what are the different things that the restoring force which is set up in the spring is equal to the weight. Okay. And that weight, we find out the weight by the formula mg. Okay. So once you get the weight, then you can use the Hooke's law. The formula is also called as the Hooke's law. F equals to kx. Okay. Where F is the force, k is the spring constant, and x is the extension produced. So this is all that you have to know over here. Now there is little bit more about the potential energy of pendulum. Okay. So I would just like to ask if any of you can explain the energy transformations that are occurring during a simple pendulum.
Like at the first, it's at rest.
Yeah.
At first, it's at rest.
This is a simple pendulum with a pendulum bob, and it moves, it oscillates between two extreme positions.
Kinetic energy.
Yeah. So how, see, now how I'm interested about it. So these are the positions. These positions, I call this position A and B as extreme positions. Okay. A and B are extreme positions. And I find out the median position, which we also call as the mean position. So you have here mean position. Okay. Now, if you observe this bob carefully, if I take the bob to either side, so as the pendulum reaches one of the extreme points, when it reaches one of the extreme points, so its velocity reduces to 0. Then again, when it comes down, its velocity increases. When it again goes to B, its speed again decreases. From at B, it becomes 0. Then again, it increases in the downward direction. right? So in this way, we observe that the speed is not constant. The speed is changing. Okay. So can you tell me at which point it should have the highest kinetic energy?
When it is at A and or B.
No. It will have the highest kinetic energy when it is at the mean position. Okay. As you know that the formula of kinetic energy is given by 1 by 2 mv square.
Hmm.
So it will be moving fastest when it is at the mean position. When it's at the extreme position, it does not experience, it has zero kinetic energy. We'll continue discussion from here. Bye everyone. Take care
By
and enjoy studies. Okay. So do not think that you will be learn everything in one day. Take some time.